We discussed in our prior lecture the idea that alkenes are basically bases, and we were able to show Markovnikov and anti-Markovnikov addition, where we have the halogen or whatever our nucleophile ultimately is, attack the more substituted carbon or the less substituted carbon. That's Markovnikov and anti-Markovnikov respectively. We saw we could do that to generate halides, and we saw we could do that to generate alcohols. Uh, Analogously, you'll notice you can also make ethers, and that's not really worth going into too deeply because you'll notice that up here what we used was water, and so you end up with an OH, and if we use an alcohol, you end up with an OR group. So the mechanisms are actually totally analogous, and I'm going to declare victory on that one as well, because really just pretend like instead of an OH, you get an OR. The proton comes from the same places, all that sort of stuff comes from the same places. Now, in the rest of these, what happens is the alkene acts more like a nucleophile. And really, if you want to get technical, the difference between a base and a nucleophile here is pretty thin. And I'm using this terminology sort of as an illustrative point. It's a electron-rich carbon source that can take protons. It can take essentially anything that comes at it as long as it wants electrons. It's not terribly picky. And so you'll notice down here that you can take this alkene and it ends up with two chlorides on it. And that's kind of strange. How exactly do you suppose that happens? And more to the point, what does that stereochemistry look like, right? Well, first let's kind of talk about what these down here are: chloride, carbon tetrachloride, bromide, iodide, all that. These are the elemental halides, right? And they are, particularly with bromide, pretty polarizable, right? Because these are, they're big atoms, and they're stuck together like this, and they've got electrons, and those electrons, they can slosh around here, and the electrons slosh around here, and so you can end up with shifting polarizations that nucleophiles don't particularly mind. So if, for instance, these big guys are just throwing the electrons over there, and this nucleophile comes up and it's like, hey, buddy, um, it can attack one bromide, and then that bromide can push its electrons over to the other side. And what you end up with is the nucleophile actually ends up with a bromide on it, and you get the Br minus. Of course, a lot of things where your nucleophile is like, say, water, for instance, can just go and that can attack the bromide, and then that can go back here, and you'd end up with some sort of equilibrium. But in the case of a double bond, what you end up with is something similar to your mercury example, or mercury example, where you have a double bond that attacks your bromide, and that kicks over electrons onto that, and then you end up with a bromonium ion that kind of looks like this. All right, and that bromide, that's a big atom. Pretty well established that now. In fact, just put that out there, and that's a big atom, right? And so you've got this structure. Now, just like in the mercurium ion, there's a positive charge collectively. That positive charge sort of exists globally over this whole thing. We'd like to pretend really that positive charge is more located closer to this side of the bromonium ion and on this carbon. That would be the location of most of that positive charge. And I had said that electron was going over there, which means that there's a bromide somewhere out here. Now, bromide, of course, Br minus, wants to get to this positive charge. That positive charge is mostly located on the carbon, so the bromide is going to find its way around, and then boom, attack there. This bond right here can go and collapse over there, and then what you end up with is the formation of a vicinal dihalide. All right. And you'll note, of course, that there is some stereochemical consideration. Just like we had covered previously, you're going to end up with the addition on one face, on opposite faces. So another way, perhaps, to look at this is let's draw our alkene in 2 dimensions, where the methyl group is coming out towards you and that hydrogen is away from you. And then there's a double bond here, and then that hydrogen's coming out towards you, and that hydrogen's going away from you. And then, of course, you've got your pi bond. So actually, I can delete one of these. And I can draw a pi bond in. The pi bond is in the plane, of course. All right, and then there's electron density here and here. Now, if I repeat this reaction, same sort of thing happens. You've got this big old Br. It's got another Br over here, and you know, it's a Br, and then that these things are kind of like, hey bud, doink, and then that's like doink. All right, and so what's really happening is the pi system, you know, it's not really attacking from one carbon or the other. It's just sort of situating itself, or like you know, like that, right? I guess, maybe, I don't know. That's how I visualize it, I guess. And so what you end up with something is that this sort of now is kind of drooping down, and the hydrogen's kind of drooping down here, and you know, you got your hydrogen here, and that one's sort of drooping down here, and then you've got your pi orbitals still kind of there. They're just sort of like bending over, and then there's this bromine sitting over here, like, yo. And this whole thing is sort of confused. There's a positive charge, more or less, on that carbon. You know, that's mostly where the positive charge is, but, you know, the positive charge is sort of distributed in this little triangle right here in real life. There's just a lack of electrons in that area and a formal positive charge. And then you've got another bromide over here. Now that bromide, of course, needs to go and attack the corresponding orbital, right? So it needs to approach an actual orbital in order to make a bond. And we've always sort of illustrated it. It's like it's attacking the back lobe of this pi system. And, you know, technically that's not 100% true, but it's accurate enough for us to draw a picture in sophomore organic chemistry, where this bromide needs to go and make a decision, all right? So it decides, no, it cannot get to any of those orbitals. There's a big fat bromide in the way, and, you know, that's a no-go. So then the bromide comes over here, and it has made a choice, right? It has made a stereoselective choice. It's not going to be able to attack on the same side of the bromide. Now it has to make a regioselective choice, either to attack on the more substituted carbon or the less substituted carbon. And I've been sort of hammering home that there's more positive charge, more electron deficiency on the more substituted carbon. Essentially, that's going to produce your more thermodynamically stable position. And so instead, this bromide, or any nucleophile really, is going to attack right there. And that is going to then kick that bromide that way. And what you're going to end up with then is a bromide on both sides here, and a bromide down here. And then this methyl group, and that hydrogen, they're both going to go up because that bromide is going to push them up. Of course, the methyl is still going to be facing you, and that hydrogen is still going to come out. Then the other side doesn't really change. There's still a hydride coming out towards you, or hydrogen and a hydrogen going away. And so that is essentially how you end up with the stereo and regioselectivity of a halide addition. And that's true enough for pretty much every halogen, is that you end up with this anti-addition of 2 halogens. Now, if you had done this reaction in water, which presumably would have been a stronger nucleophile than Br minus, or chloride minus especially, instead of this being bromide, you can easily just imagine this now being a water. All right, so we'll just make the water H2, right? And bromide's still out there, but bromide's going to be outcompeted pretty handily by water, and so I'm not as good of a nucleophile. I'm just Br minus is water, and water is going to make the same exact sort of decision tree. It's going to approach not from the top, where it would be obstructed by a halogen. Instead, it's going to do the same thing. It can come in from the bottom, and it can either pick the electron-richer orbital, or it can pick the electron-deficienter orbital. And so when that happens, of course, your product is instead the exact same thing, essentially, but instead of a dihalogen, it is a halohydrin. And a halohydrin right here. And so that is, and you get these things. This is actually a bromohydrin, and there's also something called chlorohydrin and iodohydrin. They're all part of a hydrin family. Actually, chlorohydrin, very famous old-timey drug. And all that stereochemistry and all that regiochemistry is essentially explained in the exact same way. So in these two instances over here, what you have are the vicinal dihalides explained, but what this chart doesn't necessarily do, in fact, it doesn't show any stereochemistry. In real life, those would be anti to each other. So I would probably say, if you're going to draw it, maybe I can go and get here, maybe I can go down here, make that huge, and go, let's just do that. So what I'm then going to do is actually draw it so it's sort of like, let's change our, maybe we can draw something that looks a bit more like, you know, like this. We'll say, because that's the example. I like bromide way more than I like chloride. I don't really have a good reason to actually do that, but I just do. And then I'm going to sort of draw those two. Those are the methyls, aren't they? Those methyls go there, and actually there's a methyl kind of that's over here. And you know there's no actual R and S with this particular configuration. At least there's no R or S on that one because it's got two methyl groups. Although you could definitely assign an R or S configuration to the left one, but the point is, in stereochemical assignments, is you end up with an anti-configuration. That's the stereochemistry you want to drive home. Not everything stereochemistry is about R and S. Sometimes it's about syn and anti-addition. And then the regiochemistry is pretty well explained in this particular case as well, because you ultimately end up with your initial halogen ends up actually on the less substituted side because the attacking water goes for that carbocation. That's the one that's looking for the more substituted. So that is actually illustrated correctly, even though it's sort of still missing the, it's got the regiochemistry correctly illustrated. It is kind of missing the, I would argue, the stereochemistry, but that's okay. We covered it. And so we're going to say bully on those. Now, in addition to making some halohydrins, and so what you want to keep in mind, of course, is that what I'm doing, what these lectures are actually now focused on, is teaching you how to play with Legos, molecular Legos, how to really build atoms. And there are things that you have to remember and you have to do, otherwise you can get pretty dramatically different results. Now, one thing that double bonds do pretty well is undergo oxidation. And oxidation, the way I'm going to show it to you, is essentially not too terribly different than, say, it's just attacking a nucleophile. That nucleophile just happens to be oxygen. So oxidation products give you essentially your epoxides. And epoxides are three-membered rings with an oxygen in them. The vicinal diols, and you can tell what those are. Those two oxygens are vicinal to each other. So vicinal is just a fancy pants word for saying right next to each other, distinct from geminal, which means they're twins. They're on the same carbon. Vicinal diols, that's another way of doing it. And then there's the oxidative cleavage products like aldehydes, and all of these you'll note have lots of oxygens in their reagents. Look at this right down here. RCO3. That's a lot of oxygens. That's in the epoxidation. That comes from an epoxide, and that forms an epoxide starting from a peroxide. And vicinal diols both occur through osmium tetraoxides, lots of oxides there, and manganese. Is also a strong oxidant, although in the presence of sodium hydroxide, it gives you vicinal diols. Over here, you'll notice ozone, so you would be sure to believe that you're going to do some oxidation with ozone, and then potassium permanganate in the presence of acid, as opposed to sodium hydroxide, which is base, actually gives you 2 carboxylic acids from this. Well, this would only be 1 carboxylic acid in this particular case, but you get the idea. Actually, in this case, it should be perfectly clear. This would still give you 1 ketone and 1 carboxylic acid. And we will discuss all of these in just a second. All right, the first thing we're going to look at is essentially the formation of the epoxide. So the epoxide formation is probably the most, relatable. And epoxidation or oxidation occurs with something that depends on, who you are. Either you are an oil rig person, oxidation is loss, reduction is gain. And then there's the other one. What's the other one? Leo, the lion, says grr, right? Loss of electrons. Gain of electrons? Let's just stick with oil rig. I'm not sure what the other one is. Oxidation is loss, reduction is gaining, right? And so in order to do an oxidation, you need to lose your electrons. And, oh, look, it's an alkyne. And, whoa, it's got extra electrons that it's basically ready to lose. And so you have to come in then with an oxidant. And that oxidant, you can take carboxylic acids, right, and treat them with a peroxide. You can actually create a peroxy acid. And peroxy acids are essentially hydrogen peroxide, but they're soluble in organic reagents, all right? So some pretty common organic soluble oxidant is perbenzoic acid, and perbenzoic acid looks like this, and you can buy it in a bottle, and it does a great job at being basically hydrogen peroxide, but soluble in things like tetrahydrofluoran or other common organic solvents, all right? And what this is going to do is, I've already shown you up here, it's going to make an epoxide. So how does that work? Well, you've got your double bond, all right? And so we're going to do this in 2 dimensions because I think that's probably the best way to sort of illustrate these sorts of things. You've got a H out there, H go. Ooh. Let's do that again. H going away from you, H coming out at you, and then of course you've got a double bond, and that double bond I draw as pi orbitals, and those pi orbitals have electron density. All right, and let's do it down here. Let's just draw this down here, where you have peroxobenzoic acid, and that goes over here, and you've got an oxygen, and then that oxygen, and then that goes off to your peroxobenzoic acid, and that I think probably we should just make sure we keep that white, because that business back there, all that's really doing is keeping things soluble. Now, oxidation reduction reactions kind of follow a little bit, they can do a little bit fun stuff, right? So in this process, what you do is you actually end up attacking, either you can do an initial deprotonation, or you end up attacking the oxygen. All right, and that attack on the oxygen actually ends up kicking those electrons back. All right, and then this thing floats off as some kind of carboxylate. All right, so that's just O minus. And so floating off there. So essentially, once we've got that, that comes off, that's gone. All right, and so what then happens is you end up with something there. All right. And this is going to, this thing's going to sort of start orienting itself like, it's going to start to interact with those orbitals right there. All right. And so it is forming a complex there that is very analogous to our bromonium and stuff like that, except a big difference is it's not charged. Well, it is charged. It's plus, right? So that's got a plus charge, just like our bromonium. How do you get rid of the plus charge? Whoa, that's easy. Actually, as it turns out, you just take this thing and it goes like so. And that's an H. It grabs it and off it goes. You end up forming your H in the back. That H is coming out towards you. H in the back. Methyl's coming out towards you. And then you have your new sigma bonds to an epoxide. All right? And that is how you get an epoxide. Okay? So there is a wee bit of the mechanism is a little bit funny, all right? And that basically get a combination of the electrons from the pi orbital, then collapsing on itself, and then the deprotonation of the alcohol. And so you end up with the epoxide. And that is essentially the route that you should look at when you see these things that are coming out at you. Now, that is by far not the only consequence, is that you have very specific Syn addition. So what is Syn addition? That means that the oxygens are adding to the same, or the oxygen I should say, because there's only one, is adding to the same face of the double bond. So that means that no matter what you do, you have to push whatever crap you have away from that oxygen. So let me give you an example here of what I mean by push everything away, right? So you have this symmetrical molecule. You throw in peroxide, PHCO3H, and you end up with very specific addition to the oxygen. Both of these are on the same side, and that's going to go up. And that means that those two methyl groups here, these two methyl groups there and there, they now need to go down. All right, so that is pretty important. Now, what about if you have start off with something that is in the Z configuration? I'm sorry, the E configuration. All right, what happens there? You should be ready to accept that you're going to end up with something that has a double bond that will put your oxygen right here. And then you're going to have one methyl group that's coming out towards you and one methyl group that's going away from you. And of course, there's that hydrogen that's not coming towards you and a hydrogen that's going away from you. And that's going to be your resulting configuration each time, is that you will have a starting off, if you start off with a, what do you say, trans double bond, you will end up with a trans ester. All right. If you end up with a cis, start off with something that's cis, or a Z, you will end up with something that produces the same substitution pattern in these reactions, owing to the mechanism. All right. Now let's say you all produce an epoxide. That's pretty neat. Epoxides are actually very, very useful. Epoxy resins and epoxide glues are pretty ubiquitous because epoxides are really reactive. You can see that this three-membered ring is probably not happy. Single bonds, sp3 hybridized bonds, which these technically should be, like to be 109.5 degrees. And this is an equilateral triangle, so that's like a 60-degree bond. That's pretty crazy. That's a pretty substantial amount of strain. So one cool thing with epoxides that they undergo is if you can make that ether oxygen, so this carbon, oxygen, carbon, that's called an ether, and the whole thing's called an epoxide. If you can make this oxygen want to break up with the carbons, it'll do so pretty easily. And yeah, so all you have to do really is just toss in a little bit of water and a little bit of acid, and you will end up with, let's scoot this over, a process that, well, let me illustrate it for you. You'll end up, this oxygen will deprotonate the water, or it'll deprotonate the acid actually. That's a much easier thing to do, actually try to protonate an ether with that. And what does that look like? So it looks like that. Copy and paste. So you end up with this thing like protonated, and you're back to your positively charged epoxide ring. All right, and then your water. And we can make that a slightly different color, I think, over here, just to sort of keep things straight. Your water now, in this particular case, sort of made a bad pedagogical choice, I guess, in making these symmetric, but I suppose you can probably guess which one it would choose if it had an asymmetric case, but it can come in and then it can attack that carbon, or because this is a symmetric molecule, as in they both secondary carbons, could attack that that side. Either one, equal chance. Let's say it attacks that side. Then these electrons that form that bond will go back over there, and that'll make that positive charge go away. And so your final product is actually a way to get to a diol. All right, except you'll notice how I've gone and drawn this. Your alcohol on this side is going to be over here, because you can't attack, you have to attack from the opposite side. So this is what I would say is pretty close to like an SN2 type reaction, where the orbital, the antibonding orbital that it's attacking is actually 180 degrees from the leaving group, which means that your attacking oxygen is 180 degrees from your epoxide oxygen. All right, so you're always going to end up with a syn. You're going to give an anti-hydroxyl compound, dihydroxy compound. All right, starting from a syn dihydroxylation. Sorry, a syn dihydroxylation requires both OH groups to be delivered from the same face. That isn't happening here. This particular process gives you those vicinal products in an anti-configuration, as in they are being added to different faces of the original pi bond. Okay? Now, let's say you're feeling squirrely and you actually wanted to have this product, except you wanted the two oxygens on the same face of it. You want to add both to the same face of the double bond, right? So this is a great way to add them to different sides, right? And we're using the geometry of the double bond to sort of squirrel away the functional groups we're adding. So, and the easy way to do it is to first add something to one side, and then that blocks that side, and then come around and attack. Like we've done that several times, right? We added an oxygen on that side, so that side's now occluded. And so essentially once that side's blocked, you have to go to the other side. And we've seen that happen a couple of times. So how do we get things to react? And let's go back up here because we've kind of, that's not really on our list. The trick that I just pulled to make an epoxide into a diol, a vicinal diol, but if I'm going to add it right here because it's a bit of an important little trick here. And that's going to be H plus H2O, and that will give us vicinal diol. But very different stereochemistry than these reagents. And so you got to think about it. If you want the alcohols on different sides, then you're going to add something to the first side, and then you're going to add something again to the other side through blocking one face. If you want them to be on the same side, all the oxygens, or in case both of the oxygens, have to be delivered to the same side. So if you want something like this, where your oxygen are going to be on the same side, and you know, you've got a double bond and a double bond here, you're going to need to find a way to simultaneously bring both of these oxygens to the same pi phase. So let's look at what an oxidation route that we can follow. Let's once again draw this in 2 dimensions. So that's coming out towards you. That methyl group is coming out away from you. And of course, there's a hydrogen coming this way, hydrogen going this way, and let's draw our pi system now. And one way to do that is with osmium tetraoxide. Now, osmium tetraoxide is super expensive. It's super blindy. Like, you get it in your eyeballs, you go blind. So, in fact, you get the gas that it generates into your eyeballs. You can go blind temporarily, at least, if not permanently. And I always think of osmium as being green for that reason. Now, osmium tetraoxide can come in, and osmium's got lots and lots of oxygens. Osmium can become super oxidized, right? And so what happens in this particular case is both of these oxygens are then delivered to the same face of the pi bond. And this orbital can go and grab that oxygen, and then that little oxygen pi osmium bond can go there, and then that can attack here, and that creates this osmate ester. And what you end up with then is a product that then places that methyl group kind of bends down. In fact, that's your H, that's your methyl group, that's an H back there, that's your methyl group, and now you have, I'll just switch that to an oxygen, ooh, my oxygen should be red, oxygen, oxygen, and these now produce single bonds to your osmium. So this is what you call an osmate ester. And that ester, well, it's kind of different from the first osmium, right? So if you look at this osmium, the osmium started off actually ended up inheriting some of the electrons here from these this double bond on that oxygen. It threw some of the electrons back on the osmium. In fact, it threw 2. So the osmium has been reduced. The double bond, of course, has been oxidized. And so if we want to get to our diol, we want to get that osmium off, what we have to do is actually oxidize the osmium back off. And we just toss in a little H2O2, and boom, we end up releasing our osmium. So oxidation of the osmium from the to get it back to its original lots of oxygens form, and those 2 hydrogens here, they're nice companions on those things. And so that is how you play with osmium. What's convenient about this is, like I said, osmium tetraoxide is poisonous. It's bad for your eyes, especially if you get it in there. And believe it forms a green vapor, actually. And it's expensive. So you actually only need a catalytic amount, right? Because it starts off, in fact, just really drive home that's a catalytic amount. I'm going to show that you, it's kind of like the way I drew this. Copy, paste. It comes right back here. Not with a blue arrow, of course, but you get it back. So osmium tetraoxide, it's a catalyst, and it helps you generate alcohols that are on the exact same side of the double bond. So that's pretty sweet. You can create the same exact product with potassium permanganate and base. And the base is super important. In fact, so is not doing this at high temp. You want to keep this at low temp. Actually, everything up to this point is the same, but you use permanganate or manganese. That's Mn. All right. And you end up with the exact same structure. And if you want the exact same product, you just throw in alcohol, hydroxide, specifically hydroxide because you're in base, and you can kick that out and you will slowly peel off your manganese and get to the same product as long as you are in base. All right, that will pop that off, and then another equivalent of hydroxide can come in and do the opposite to the other side. Now manganese, permanganate, potassium permanganate is more well known for its ability to split that bond, that carbon-carbon bond, to give you two aldehydes in this particular case. Yes, two aldehydes. And how that happens is if you are in a solution of acid, so there's no base, so this isn't going to happen. What permanganate likes to do instead is to break up bonds. That carbon come and form there, and you'll end up breaking that back down there. And so instead of forming a fissional diol, you'll end up with actually just the aldehyde. And you'll note that now this should have two bonds, so that's your double bond there. And actually you make the same thing on the other side, so you end up with two of them, because it's a symmetrical molecule, isn't it? So there you go, you end up with two aldehydes, except the big thing with potassium permanganate reactions is, good luck controlling how much permanganate you add. You need very little, and this aldehyde, bam, it becomes, well, wait, no, running out of room. Bam, there we go, that way. Becomes a carboxylic acid. So if you wanted an aldehyde, you're not going to get an aldehyde. Now with potassium permanganate. There's just no way to get an aldehyde. But if you do want an aldehyde, let me just emphasize again that this happens in neutral solution or even acidic solutions of H+, and any amount of heat really will kick this whole process off. Actually, over here, any amount of heat, and you'll get that carboxylic acid product. So that comes back up, and that helps explain this bit up here. Now, there's a couple last little bits. Now, ozone is another route to get to aldehydes. Let's say you just want to stop at aldehydes. All right, aldehydes are also very useful. H, methyl group here, methyl group there. Now we're going to add our pi bond here, pi bond there. And an ozone molecule. So we've seen these ozone molecules. They're bent. Oxygen O, O minus. So plus here. You can kind of see that ozone's pretty much begging for this sort of chemistry, where that goes and does a reaction on that orbital. And then once that happens, you end up with these electrons going and attacking that oxygen, and then those electrons going and falling back on your oxygen in the middle. And then what you have here is now the hydrogen is still pointing towards you, but it's now bent up. That methyl group is now on the back. This methyl group still pointing out towards you, now bent up, and then that hydrogen is now on the back. That's a hydrogen, by the way. And what you have is this funky, this 5-membered ring. And that 5-membered ring's not very stable. What it pretty quickly does is breaks. And you need another electron to come down here, and that's gonna make it mad. So one like normal, and then one that's a negative, that's a positive charge, and that's not long for this Earth. And so what this ends up doing is it can just do a flip. And then you end up with an attack on there. Well, end up with initially an attack on that carbon, and then that oxygen attacks there, and then that attacks back onto that oxygen. And so you end up with an ozonide. The ozonide actually is a bit more stable. In fact, it's very stable. You can isolate it. The oxygen is connected to oxygen, so that's these two oxygens right here. And those down to your carbons. Actually, that's your carbon. And those have your methyl group coming off of it. That's your carbon with your methyl group coming off of it. And then those go back down to another oxygen. All right. And so how do you get rid of these? Well, that's a pretty oxidized molecule right there. And in order to get it down, you're going to have to throw in something that's going to reduce it. And so one reducing agent that helps get this back down to aldehydes is just an incredible smelling thioether. All right, and essentially, the sulfur loves oxygens. It's yearning to be oxidized. And it will be happy to take one of these oxygens off the hands of the ozonide. To create our 2 aldehydes. An aldehyde, so it's got an oxygen there. And 1 DMSO, dimethyl, these two sulfoxide, which is what that functional group is. All right, and so depending on your oxidation strategy, you can end up with epoxides. And epoxides, of course, can open up to form different kinds of alcohols. If you would like a syn alcohol, you would go through an epoxide. But if you want if you want an anti-alcohol, you go through an epoxide. Those would be alcohols on the opposite sides. If you want a syn alcohol, syn vicinal alcohol, you have to go through osmium tetraoxide. That's your safest bet. Now, you can also use manganese potassium permanganate. That is a brain fart. Potassium permanganate in the presence of base, and that'll also give you vicinal diols that are on the same side of the double bond. But if you are not careful, you'll pretty quickly end up with making carboxylic acids by cleaving there. That's pretty easy to do. And you can, of course, if that's your goal, if your goal is actually to take an alkene and start making aldehydes or ketones, then maybe you should consider ozonolysis as a path to cleaving double bonds and starting to form ketones and aldehydes. And so those are different routes that you can take. Now, for some reason, what if you wanted to go back to just a straight alkane? All right, and so we've got two alkanes listed right here. We've got cyclopropane, and then we just got back to like the normal alkane, right? And just going back to normal alkanes is pretty simple. Like this is a pretty simple reaction. It's just called a hydrogenation. Hydrogenation, drawing the mechanism for that's weird. This is actually what you call a heterogeneous reaction. The palladium is going to be starred. You're going to use a noble metal. Palladium, palladium's a precious metal, so it's going to be like gray or something. That's going to be like palladium metal. It's big metal, right? Palladium metal, it's extremely expensive too. It's going to be stuck on like carbon, like a carbon, like charcoal, right? And so you're going to take this stuff and you're going to throw it into a solution of solvent. It's going to make it black. It's going to look like you've got charcoal in solution. It is not really dissolved. It's just in solution. But what's neat is you got a double bond, and let's say methyl group coming out towards you, and H. It's got a pi bond. What's going to happen here is these pi bonds, like palladium, loves pi bonds, and it also actually loves hydrogen gas. And so this thing's gonna be like, ooh, metal, doink, 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 doink. It's really gonna be interested in that metal. And palladium, if you add hydrogen gas to it, it just starts getting all kinds of hydrogen. Like it'll break the hydrogen and it'll get a surface filled with hydrides. And so what you end up doing actually is this hydride-rich surface, and this pi bond is just kind of like doink, 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 and it will eventually actually react, and you will end up with the hydrogenated or the reduced compound. You'll end up taking that, and that'll be like, I'll take that, and then it's like, fine, then you also have to take that, and you end up with just propane. Not a particularly exciting thing, but it is a great way to go from a double bond to a single bond. All right, that is hydrogenation, easy peasy. Cyclopropanes are pretty interesting, and those go through a carbene intermediate. And we had talked about carbene intermediates a little bit, and let's have a quick chat about those. So essentially what you're looking at is a double bond. You're going to add one carbon to your double bond. And so you got methyl, H, just, we're going to keep this pretty simple. Kind of donked it up a bit. Yeah, let's definitely keep this a little simple. And you got pi cloud, electron. How do you add just one carbon to your double bond? And the approach is through carbenes. So, and we had discussed carbenes. They're just carbons, right? And they actually have an empty pi orbital. So, well, pi orbitals are always orange, aren't they? So they have an empty pi orbital, which is weird. And that's kind of like a positively charged pi orbital. And then they've got, sp2 orbitals, one orbital over here that's coming out towards you, one orbital is kind of going away from you, and one just facing out. And then that empty sp2 orbital, they've got 2 electrons. So it's like a positive and a negative charge all put onto one carbon, right? So it's both kind of an electrophile and kind of a nucleophile. And so if you take one of these things, as nutty as they are, they're going to sort of do one of these, and they're going to add to the same face, right? So this seems like it should make sense that those two are going to come down here, and then the electrons that are in the pi bond are then going to fill in that empty orbital, and then you're going to end up with your epoxide. And your epoxide is just fancy words for, I'm sorry, I keep saying epoxide. What I mean to be saying is cyclopropane. And you're going to end up with cyclopropane. And maybe it's worth reviewing exactly where that goofy thing came from, right? So there are a couple of ways to produce carbon carbenes, right? And we had covered that if you want to make a carbene, you can start off with carbon that has a bromide and H. And if you take an alcohol, and deprotonate it, and you've got a hydroxide, it can come in and deprotonate, right? So that's how you get a negative charge. So now you've got a carbon with an H, a Br, and then a negative or an empty, or I'm sorry, a filled sp3 orbital. But instead of going off and doing some crazy stuff, what happens is it actually just kicks off its own bromide, right? And it pops it off in a way that basically just boots it right out. It totally rehybridizes from sp3 down to sp2 because now the carbon has vacated its own orbital, so an empty orbital is essentially just a pure p orbital, and that makes it a sp2 hybridized carbon. And it's still got this orbital also that's got electrons in it. So that's kind of strange. And it's also sp2, so it's got something coming out towards you, and those would be just hydrogens, right? And so that's how you can generate a carbene. It's basically a carbon source with one empty orbital that's plus and one filled orbital that's got electrons, and it can undergo that kind of attack. Another way that's somewhat analogous is instead of using base, you can actually just use a little trick that forces the H's off, and that's diiodomethane in the presence of zinc cuprate, and that also will generate the same species. And you'll notice that again you end up producing a reaction that occurs on the same face. So if you start off with a cyclohexane and it's got two methyl groups, it's going to end up pushing those two methyl groups down because the carbon is going to add to the same face. Let's just rotate this so that now we've got this, and that's going to be in the back. That's going to come out here. That's out here and here, right? And so your pi orbitals are like that, and it's like that, and then you're going to come in, and it's got this thing right here. Actually, I'm just going to think it's going to float down like going to come in, and it really, you can't really imagine how it's going to approach any other way. Now you'll notice it can go in the top, it could also go on the bottom. There's no selectivity there, but the selectivity all comes from the fact that it's going to end up reacting on the same carbon, on the same side. So the stereochemistry is along the lines of you get effectively Syn addition of your carbon. You know, it's just like one carbon. And those two now pop up, and now you've got that. So your product is, I guess, if I were to draw it maybe a little bit more clearly, methyl groups coming up, CH2 groups going down. And that is the last of the reactions that you need to know and the mechanisms for this chapter.